Welcome to this video and welcome to Discrete Learning Institute. Here we learn easily and we learn fast. So whatever concept is giving you problems, here we're going to simplify it so that you understand. Okay, so today we'll be looking at probability theory. And with me here, I have tutorial sheet questions, okay, that are going to help us understand concepts in what? In probability theory. Okay, so this tutorial sheet here covers a lot of concepts, okay, in probability theory. So we're going to start from the definitions of the terminologies that we use in probability theory, like the sample space, uh, conditional probability, mutual exclusive event, independent events. We're going to define all these that you can see there in simple ways. Okay, we're going to see how we can come up with the sample size if we're given an experiment and also represent the sample size on tree diagrams. Okay, we're going to move on and look at the basic probability calculations. Okay, so the ones that do not involve any tables, we just calculate them directly by using like the complement rule, independent selections, the multiplicative rule, and the like. We're also going to look at probability on two-way classification tables, and that will involve conditional probabilities, independence, and mutually exclusiveness. Okay, so we're going to look at all that Bayes theorem. We're going to look at that. We're going to look at the probability distributions, like the binomial, the Poisson. We are going to understand all that. And I have a lot of questions here, as you can see, which are going to actually help us understand all the things that I've mentioned here. Okay, so we have a lot of questions here. You can see 23 questions, and we're going to solve each and every question in here one by one. Okay, so let's start our discussion. All right, so we look at the first question here. They're saying, give the meaning, okay? Do I have my pencil? Give the meaning of the following terminologies as used in probability theory. Okay, so just like statistics, we needed to learn some of the terminologies that we'll be using throughout statistics, right? So it's the same with the probability. We need to know some terminologies before we can be able to answer some questions and the like. So there's a list here of terminologies that you'll be using in probability theory. So they want us to give the meaning of each of these what? Terminologies. So it's very important to understand the terminology because it will make the questions simpler for you to actually understand what they're talking about or what they're asking you on. So we start with the experiment here. So I was writing down the definitions so that you can also be reading through them as we discuss them. So we start with the experiment there. Okay, so what is an experiment in probability theory? Okay, so an experiment in probability is simply a process or an action that produces results. Okay, so any process that will produce result or that will produce outcomes is what we are calling as an experiment. Okay, so these results, okay, cannot be predicted with the certainty in advance. So we are doing an experiment because the results that we are going to get cannot be predicted with certainty in advance. Okay, so this experiment must be repeatable. We must be able to repeat the experiment a number of times, and then that experiment should produce at least one possible outcome. Okay? Must produce at least one possible outcome. And then the experiment should have uncertainty because we do not know. No wonder we are performing it. So an example to just understand the definition, I've given two examples here. So the first one is if you go at the hospital, for example, okay, and then you're trying to test this patient for malaria. So there are two possible outcomes, right? After you do your test, it's either that patient is going to be positive, okay, or that patient is going to be negative. So that testing a patient for the malaria is what we are referring to as what? An experiment. Okay, so there are two possible outcomes. There are either the patient to be positive or the patient to actually be what? Be negative. Okay, so if a patient just comes and then you just suspect that the results, okay, you just suspect that, okay, this patient might have malaria, then it will just be like a guess, or it will be like guesswork, and you won't be 100% percent sure that that patient has malaria unless you test. And that test is what you're calling as what? An experiment. So this is what I was meaning here, that the results of that experiment cannot be predicted with certainty in advance. You can only be certain after you do what? The experiment. In this case, I gave an example of testing a patient for malaria. Okay, so another example of an experiment is tossing a coin. So if you get that 1/4 coin, for example, okay, there's the part that we call the head, like the front part, and then the other part, which is at the back of the coin, we call it as the tail. So if you get that coin and then you toss it, you're conducting an experiment, okay? Because from that toss that you've done, you are going to end up with two outcomes. So that this coin is going to land on the head, or this coin is going to land on the what? On the tail. So you're conducting an experiment. You have at least one possible what? Outcome. But as you toss the coin, you can't be sure where it's going to land. Okay? You can't be sure where it's going to land. So no wonder we're saying this experiment cannot be predicted with certainty in advance. You are not sure until it lands, then now you'll be sure, okay, it has landed on the head. Okay, so that's the definition of what the experiment is. Moving on, we talk about the outcome. Okay, so an outcome is just a single possible result of an experiment. Okay, so once you are performing that experiment, for example, tossing a coin, if you obtain head, that's an outcome. Okay, and the tail again, it's an what? Outcome. If we use that example I gave for malaria, then the outcome will either be positive or what? Negative. So an outcome is just a single possible result of what? An experiment. Okay, or sometimes you can say an outcome is one element which is inside the what? The sample space. Okay, so now what is the sample space? The sample space is just the total possible outcomes of an experiment, right? That's what we call as the sample space. So for example, this set that I've given here is called a sample space for tossing a coin, because it contains all the possible outcomes that can come out from that experiment. All right, moving forward, we define a sample space. I'm just from talking about it. So a sample space is the set of all possible outcomes of an experiment. And in most cases, the sample space is going to be denoted by the letter S. Okay, so same example that I was giving there, tossing a coin. So what are the total possible outcomes? It's either the coin lands on the head or it lands on the tail. So now when you get all those outcomes, you put them in one set. That set is what we call as the sample space there. Okay, I can also give another example. Let's say you go at the hospital, you want to check your blood your blood group, right? So the total set of all the possible outcomes that you can either be blood group A, or you can be B, or you can be AB, or you can be O. So the set that is going to contain all those possibilities for your blood group is what we are calling as the what? The sample space. Okay. And then also you can have a situation where you're tossing two coins at the same time. Okay, let's say you have a 1/4 coin and then you have a 50 ngwe coin. So you're tossing those two coins at the same time. So when you toss, it's either both of them can land on head. So I get head, head and head, or one can land on head and then the other one lands on the tail. Okay, or one can land on the tail and then the other one lands on head, or both of them can land on the tails. So if you are tossing two coins at the same time, then your outcomes are going to look something like this. And then when you get all these outcomes and put them in one set like this, then you form a what? A sample space. Okay. Moving on, we look at the simple event. So if you have any question, guys, please just unmute yourself and then you ask. So what is a simple event? Okay, so just from the word itself, it's saying simple. So a simple event is an event that contains only one outcome from the sample space. So you have this sample space that contains possible outcomes. And then if I just get one outcome from that sample space, I make it as my event, then that event is going to be called a simple event. Okay, so it's simple because it cannot be broken down into what? Into simpler events. So for example, if my sample space is this for tossing a coin, and then I just get one of those outcomes, and then I form another event like that, then that event that I've formed is what? Is a simple event. Okay, so a simple event is an event that contains only one outcome from the what? From the sample space. All right, and then from there, we have to talk about the opposite, okay, or the complement of the simple event. So that is what we call as the compound event. Okay, so a compound event is just an event that contains two or more outcomes. Okay, so if a simple contains one, then a compound should contain two or more outcomes. Okay, so for example, if this is your sample space here, you can see it has how many outcomes? 1, 2, 3, 4. So we're going to call it as a compound um, event, okay? Or from this same sample as space, you can just collect two or more outcomes. You make an event. You're also going to call that as a compound event. So a compound event will have two or more what? Outcomes. And I've demonstrated there. Okay, the other definition that we had was equally likely events. So equally likely events. So it's in the word itself, right? So events that are equally likely, okay, to occur with the same probability are what we call as the equally likely events. Okay, so events are equally likely if each outcome has the same probability of occurring. And a good example here is when you have a die. So if this is a die here, I don't know if I'll draw a good example. Yeah, so this is a die, right? So we know that a die has six sides. So I can have one on top, two here on the side, three on this side, and then four on that side. Okay, and then five down here, and then six there at the back there. Okay, so here the probability of getting a one when you roll this die, okay, will just be uh, the number of outcomes uh, or the number of ones that are appearing on this die, which is just one, divided by the total sides that are there, which is just six. Okay, but again, when we find the probability of getting a two, we just have one, two there, and the number of sides are also six. If I say again, the probability of getting a six, we just have one six there. So I'll say one over the total of the number of sides. I have what? Six. So you see that the probability of getting a one or a two or a six or a three or a four or a five, they are equal. So we're going to call those events as equally likely events because they have the same probability of what? Of occurring or happening or taking place. Okay, so another definition is what we call as subjective probability. Okay, so what is subjective probability? So subjective meaning it just depends on preference, right? Just depends on preference. So subjective probability will be a probability that is based on personal beliefs. Okay, that is based on personal judgment or personal experience, and it's not related in any way with the what? With the mathematical calculation. So, for example, if you go to the hospital and then a doctor, based on his experience, okay, he hasn't calculated any probability, then he just says, I believe this patient has an 80% chance of recovery. That is going to be a subjective probability. It's not calculated, okay? It's just based on the personal judgment and the personal experience of that same what? Doctor. Okay. Another example is that maybe the lecturer is teaching this group of students, okay, and then he sees that, okay, these students are performing very well in their what? In their assessments test, okay, in their quizzes and the test. Then based on maybe a past experience that that lecturer had when there was such a time where students were performing better in their assessments, okay, you can say, I'm confident that these students are going to pass maybe by 90%. So that 90% has not been calculated, but it's just purely based on what? The experience or the personal judgment of that lecturer. That's what we mean by subjective probability. Okay, there's nothing involving mathematical calculations, purely experience, judgment, or just personal belief. Okay, and then from there, we talk about what we call as the marginal probability. Okay, so marginal probability is simply the probability of a single event occurring without considering other events. Okay, so usually obtained from row or column totals in contingency tables. We're going to talk about the contingency tables later on. Okay, so if for example, I have um, I have 40 females, okay? And then I have 60 males. And then I just want to find the probability of males in this population, because here it will mean that I have 100 people in total, right? Because there are 40 females and 60 males. So now, in order to get the probability of the males that are in this population, I do not have to know how many females are there. Okay, I do not have to know. I just have to know how many males are there. This is what I was showing here. So the probability of male would just be the total males that are there divided by the total. It doesn't matter if I know anything about the rest of the 40. If they're female or not, it doesn't matter. As long as I know how many males are there, then I'll be able to calculate the probability of the what? Of the male. So this is what we are meaning here. We are saying um, the marginal probability is the probability of a single event occurring without considering the other event. Because the other event here would be considering the females. But we are not even considering the females, but we are still able to get the probability of the what? Of the males. So it's the same. If I also wanted, I could say probability of the female. And to find the probability of the female, I do not need the information about how many males are there. I just have to know, okay, how many females are there? There are 40. And then I divide by 100, I'll get what? 0.4. So I'm still able to get this probability without considering the probability of the what? Of the males. So that's what we mean by marginal probability. Okay, so usually you talk about marginal probability when you talk about the joint probability. Okay, so let's say you have two random variables there, x and y, and then you just want to find the probability of x. Okay, you forget about the y. That's when you talk about the marginal probabilities like that. Okay, so we're going to understand them better later on. We can talk about them in details, but there I'll just give you a definition. The other definition that we need to explain is conditional probability. Okay, we have to explain conditional what? Probability. So conditional. So meaning this probability is based on a certain what? Condition. Okay, it's based on the certain condition. So conditional probability by definition is the probability of an event A occurring given that event B has already occurred. Okay, the probability of an event A occurring given that the event B has already occurred. That's what we call as conditional probability. Okay, so like for example, if you're finding the probability of passing the exams, given that you were attending lectures, okay, that's a conditional probability. So the attending part of the lectures has already passed. Okay, it has already passed. But now you're trying to find the probability of passing the exam given that you were attending the what? The lectures. So that's what we mean by conditional probability. And then conditional probability, we're going to be uh, finding it using this formula here. So you can see probability of A, and then this slash here means given B, okay, is equals to the probability of the intersection of A and B then divided by the probability of what? B. So this is the formula that we are going to be using to find the conditional probability. Then I was given an example here, but we're going to talk about it more um, when we start solving questions about the conditional probability. Okay, mutually exclusive events. Okay, so two events are mutually exclusive if they cannot happen at the same time. Okay, two events are mutually exclusive if they cannot happen at the same time. So if these events, let's say event A and B, are mutually exclusive, then it means that the probability of this intersection is just going to be what? Zero, because they cannot happen at the same time. So meaning their intersection has nothing. So meaning that the probability of A intersection this B will just be what? Zero. So in most cases, this is the most important thing that you have to know. So when you talk about mutually exclusive event, what should come to your mind is that the probability of their intersection, those two events that you are talking about, is what? Zero. Okay, so later on you see when you are solving questions on the two-way classification tables, okay, they'll ask you, are these events mutually exclusive? So to show that the events are mutually exclusive, it suffices to show that the probability of their intersection is what? Is zero. So if you are able to show that the probability of their intersection is zero, then it means that those two events are what? Mutually exclusive. Okay, so that's the definition there. So a good example is that one person cannot be male and female at the same time. So, unlike the reports that I actually saw on ZBC where some man in Chipata was posing as a female, so that cannot happen. Okay, you can't be both male and a female at at the same time. So that probability there, the intersection is zero. So those are mutually exclusive events. If you're a male, then you cannot be a female. If you're a female, then you cannot be a what? A male. All right. Unless there are just some disorders in you with the genetics and the like. All right, so the other definition that was there, it's the independent events. Okay, the other definition that was there was the independent events. Okay, so we can even hear from the word independent events. So it means that the occurrence of one event does not affect the occurrence of the other because they're independent, right? Okay, so two events are said to be independent if the occurrence of of one event does not affect uh, the occurrence of the other or does not affect the probability of the other one what happening. That's when we say that two events are actually what? Independent. Okay, so formula wise or mathematically, we say two events are independent if the probability of their intersection is the same as the probability of the product of their what? Of their individual probabilities like that. So if the probability of A intersection B is equals to the probability of A multiplied by the probability of B, then we're going to say that those two events are what? Independent. Because the occurrence of the other won't affect the occurrence of the what? Of the other one. All right, so this is the definition here. Okay. And then this formula for independent events can also be used in the conditional probability formula. Okay. So remember the probability of A given B, we had said this was the probability of A intersection B, right? And then we divide this by the probability of what? B. This is what we said. So now if we are considering two events that are independent here, this top part here just becomes probability of A multiplied by the probability of B, right? By the definition of independence. Then I'm dividing by the probability of what? B. So you see here that B and B, probability of B and B, they're going to cancel. So I'm just going to remain with the probability of what? A. So sometimes they can ask you to prove that if two events are independent, then their conditional probability of A and B will just simply be the probability of what? A. Okay, they can ask you to prove this. So this is how you prove. You just replace this top part here, which is the intersection, with the definition of independent events like that, and then you cancel out the B, you get your probability of A there. Okay, so I just wanted to mention this. So any questions there on part one? Any questions there where we're talking about the terminologies? Okay, so thank you so much. I'm very sure that you are enjoying this video and you are understanding the concept. So I'd just like you to inform you that we actually have a platform, okay, where we have a lot of videos that can help you understand just like the way you've been understanding as you've been watching this video. Okay, so the platform is called discretelearning.com. So you can actually visit our website. So here, just search discretelearning.com here, and then you click search. It's going to take you to this website. If you don't have an account, just create one. Okay, you can check the link in the description here. It has a video that can help you create an account. Then once you log in, okay, using your details, you find these are 4 pre-med courses or NS courses. So there's math, chemistry, and biology. Okay, so you can subscribe for any course here, and then you're going to find a lot of videos. Okay, tutorial sheets, you're going to find topic lessons, and you're going to find past papers, and all that is going to help you in your studies. All right, so if you're interested, please make sure you subscribe and then be learning at your own pace. Okay, so now we look at questions where we'll be listing down the sample space and then also representing it on what? On tree diagrams. Okay, so this first question here, they're saying, list the sample space of the following experiment and then present the outcomes on a tree diagram. Okay, so we said the sample space is the set that contains all the possible outcomes, right? Okay, so let's look at part A. So part A is an event that is happening. So they want us to list down the sample space. Then once we list down the sample space, we can show it on the tree diagram. So as we're going to be doing the opposite, we're first going to be representing this on a tree diagram, okay? And then now we can list the sample space. So the first one, they're saying, picking at random 2 patients from a ward having patients with malaria, dysentery, and what? Diarrhea. So from this ward, that has these patients, some have malaria in that ward, some have dysentery, and some have diarrhea. We want to pick at random 2 patients from what? From that ward. So want to come up with the sample space for this event and also show it on the what? On the tree diagram. So for those who do not know the tree diagram, it's just a simple diagram that shows um, the probabilities of an event. Okay, so before I can even answer this one, let's look at this example. So if I toss a coin, right? I toss a coin. My possible outcomes is that this thing can land on the head or it can land on where? The tail. So now if I want to represent or show this on a tree diagram, I'm just going to write like that. Okay. And then I'm going to say, when I toss this coin, my first outcome can be a head. Okay. And then if my first, if that coin lands on the head, okay, in my first attempt, then in another attempt, it means that this thing can land on the what? On the tail. So this thing here that shows the distribution of the probabilities of a certain event is what we are calling as the tree diagram. Okay, so it's simply showing you that here we have 2 possible outcomes. So that when you toss this coin, you can land on head or you can land on where? The tail. So this here, hey, let me do this. So this here can be the first toss. Okay, and then let's say you toss this coin again. So if you toss this coin again, if it had landed on the head, okay, in the first toss, then in the second toss, it can either go again and land on the head, or it can now land on the what? On the tail. So this is the second toss. Okay, then if in the first toss you had gotten head, then in the second toss there's a possibility that now you can get the head, okay, or you can get the tail again. Okay, so what I'm drawing here is what we are calling as the tree diagram. Again, I can go on and do a third toss. Okay, so if my first toss gave me head, my second one gave me head, there's also a possibility that this third one here, okay, that this third one here will also give me what? A head there, or it can now give me a tail. Okay, so this is my third toss. Okay, what if my first gave me a head and then my second gave me a tail? Then it means there's a possibility that my third here can give me head or it can give a tail as well. Okay, and it's the same thing that will happen here. This guy here can either go and land on the head or it can land on the tail. This one, again, it can go and land on the head or it can land on the what? On the tail. So such a diagram here is what we are calling as a tree diagram. So it just shows the summary of the probabilities there. So here we're just constructing the sample spaces, so there's no need to include the probabilities there. But you see later on, as we solve the questions, we'll be putting some numbers here to show that the probability maybe of getting the head is actually half, the probability of getting the tail is actually the half. So just like that. All right, so now that we know what a tree diagram is, we can draw a tree diagram for this. Then from the tree diagram, we're going to get the sample space. So here we are picking at random two patients. So meaning there are two selections there. There's the first patient that we select, and then again we select another patient. So it's like we are doing two tosses for the coin, right? So there's round one, we select one patient, and then round two, we select another one, right? So I'm going to say, since here we have three diseases that are present in that ward, so it means on my first pick, I can either pick a person that has, okay, let me write it like this. I can either pick a person that has what? Malaria, or I can pick a person that has what? Dysentery, or I can pick a person that has what? Diarrhea. So for diarrhea, let's just use R like that. Okay, so this is my first pick. I can pick a person with malaria, or I can pick a person with diarrhea, or I can pick the person with what? With, oh, this is dysentery, and then this is diarrhea. So this is my first pick. So let's say first pick. Okay, so remember, I want to pick two people. So if that is my first pick, let's do my second pick. Okay, so now in my second pick, if my first one had picked the guy, okay, that had malaria, then in the second pick, I can pick another person also with what? With malaria, or I can now this time pick a person with dysentery, or I can now pick this time a person with what? With diarrhea. So there are three possibilities even here, like that. Okay? And then if my first had dysentery, then it's the same thing. My second can have malaria, they can have dysentery, or they can have what? Diarrhea. Just like that. And it will be the same even from this guy here. I can pick now the one with malaria, or I can pick the one with dysentery, or I can still pick the one with what? Diarrhea, like that. So this is my second pick. So here we pick one, here we pick one, and then we have the two patients that are required. Okay, and then, so that is my tree diagram. We've drawn it. Then from the tree diagram now, we can get our set what? S, which is just the sample space. So remember, we are picking two people. Okay, we're picking two people. So what would be the possible outcomes that I'm going to be putting in this set? Okay, so uh, those outcomes should have two people in them. So it's either my first pick is malaria and my second pick is malaria. So what am I going to have here as a pair? Okay, it's just going to have malaria, comma, malaria. This will be my first possible outcome of this experiment. Or it can be that my first was malaria, and then now my second is what? Dysentery. So it can be M, comma, D now, like that, comma. Or it can be my first was malaria, and then my second is what? diarrhea like that. Okay, so that would be the third outcome. That would be in this sample space. Or it can be that my first actually was this guy here decent. So now I start I start pairing the decently with everything that is there. Okay, so it will just be D comma M. I'm sure by now you know what's happening, and then D comma D. Okay, and then D comma what comma R. So these are possible outcomes. Then the other possible outcomes is when the first one is what? Having diarrhea. So it means the first one has diarrhea, then the second one can have malaria. Okay. Or the first one still has diarrhea, but the second one has dysentery. Or the first one still has diarrhea, but even the second has what? Diarrhea like that. So we said R represents diarrhea, right? And then I close my set like that. So you, when writing, don't write like the way I did. Continue from this side here, but it's just that my space is done there. All right, so guys, any questions here? Now we've come up with this sample space from the tree diagram. We can easily see it, right? Okay, we can easily see it. So no wonder I was saying we first start with the tree diagram, and then now we can go to what? To we can go to the sample space. Because if we have the tree diagram, we're able to see it will be very easy for us to construct the sample space. So this was part A. Okay, we go to part B. So part B, they're saying selecting randomly 3 pills. Okay, selecting randomly 3 pills from a bottle with red and green pills. Okay, so from this bottle that has red and green pills, we want to pick 3 pills from there, right? We want to pick 3 pills from there. And then those um, 3 pills, okay, should be picked in how many trials? 3. Because we first pick the first one, then we pick the second one, and then we pick the what? The third one. So it's like we're having 3 tosses, something like that. So let's do that. So here, the possible outcomes of every pick is that it can either be red or what? Or green. So I have this bag that has these pills. So on my first pick, I can have that. Okay. My first pick is red, or it can be that my first pick is what? Is green. Okay, so this is my first pick or my first selection, whatever you want to call it. Then now I go to my second selection, okay, or my second pick. So if my first pick was a red pill, it can happen that in my second pick, I still get a red one, or now I get a what? A green one. Okay, now I get a green one. If my first pick was green, it may happen that in my second one, I now pick a red, or I still pick a what? A green. So this is my second what? My second pick there. I've picked the second pill. So now I have 2 pills in my hands. Then I want to pick another one. Okay, I want to pick another one. So what do I do? If my first was red, my second was red, it might be that even my third here can also be what? Red. Or it might happen that now my third is green. Okay, so this thing has come from this guy. And then from this guy, again, I have the same situation. It can either be red or it's now what? Green. From this guy, same situation. It can either be red or green. And from this guy, again, same situation. It can either be red or green. So whatever we've drawn here is our tree diagram. And this part here is going to be our third pick. Okay, so here I've picked 1 pill, here 1, here 1. When I add them, I have my 3 pills that I required there. Okay, so that is the tree diagram that we draw for this experiment. So now, what would be my sample space? Okay, so let me put this on top there. So third pick. So what would be my sample space? So S will be equals to, okay? So since I'm picking three pills, then I should have three pills in each outcome, right? So my first one will be red, red, red. Okay, so it will be red, red, and then red. This is my first outcome of the three pills that I need. Or it can be what? Red, red, and then the last one is green. Or it can be red, okay, and then my second one is green, my third one is green. Okay, so I'm done with this one that is starting with uh, uh, okay, so this one is it's how? Okay, so I'm starting with red, 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 and then red, red, green, and then red, green, red. So this one here is false. So let's erase this one. Okay, so because I'm just following the order here. So it's red, green now, and then red. So I should write red, green, and then red. Okay, so that will mean that I'm done with it, starting with the no, I'm not done. There's one more. So red, green, green. Okay, so I almost forgot it. So red, green, green. That would be another possible outcome. And then now this means I'm done, right? I'm done with the things that start with red. So now if my first pick was green, then it can be that I pick green, red, red. So it will be green, red, and then red. Or it can be green, red, green. So green, red, and then green. Or it can be what? Uh, Green, but I can't go here. I've already picked two. So I'm now going here. So green, green, red. So I'm just going to write it on top here. So green, green, and then what? Red. Okay, or it can be green, green, green. So it will be green, green, and then green. And then I close my set. Okay, so that will be my what? My sample space there. So any questions there on how we are getting the sample space? Okay, so if there are no question, we move on to part C. Okay, so what does part C have for us? So part C, it's saying choosing two nurses from a group having male and female nurses. Okay, so this group has male and female nurses, and then I just want to choose um, two nurses from there. Okay, so it means I have how many selections? Two. So the first one, I can choose um, a male nurse, okay, or I can actually choose a female nurse. So this is my first selection. Remember, I just need two nurses, so I just have to make a second selection here, then I'm done. So in my second selection here, I can either choose again a male nurse, or now I choose the female one. If my first one was female, I can now choose the male here, or I can still choose another what? Female. So this is my second selection here. So what do you think will be our sample space there? To just be male, male. Okay, so I can choose two male nurses, or I can choose a male and then a female, or I can choose a female and then a male. Okay, and then I can choose female, female. So female and then female. Okay, so this here will be my sample space like that. So any questions there? Right. So if there are not some, I almost say if there are no sample space now. Okay, so if there are no questions there, we'll move on to part three. Okay, part three still has the same reasoning of the sample space plus the tree diagram and the like. Okay, so let's read the question. So they're saying in a certain group, some people love running, others love jumping, and others love press up to keep them fit. Okay, there is not even a single person who loves two or more or none of the activities. So what does that statement means? It means um, each one, okay, each person just belongs to one activity because they've said the intersection is 0 and all of them actually do something. So it means everyone just belongs to one of those groups. There's no one who loves two things, like they love running and jumping at the same time. No. So if you're in running, you're just running. Jumping, jumping. If press ups, you're just what? Press ups. That's what that statement means. So now they're saying two individuals are selected from this group randomly, one after the other. Part A, draw a tree diagram for this experiment. Okay? So what do we have? We have those who love running, those who love jumping, and then those who love what? Press ups. So I'm just going to indicate with P. So I want to select two individuals, one after the other. So it means I have how many selections? Two, right? So I'm going to say in my first selection here, okay, I can have that my first selection is those who are running, or it can be those who are jumping, or it can be those who are what? Doing press ups. So this is my first selection here. Okay, and then now I go to my second selection there. Okay, so in my second selection, it can be that I also choose another person who likes running, or now I choose the one who jumps, or actually I choose the one who does what? Press ups. And here it will just be the same thing. Okay. So I just draw three things here. So running, jumping, and then press ups. And then here for this person who does press ups, okay, it means that I can now select someone who loves running, or someone who does the jumping, or actually someone who loves the press ups again. Okay, so just draw it nicely on your papers. Here it's just the space that has finished. So yeah, so this is my tree diagram here. And then what would be the sample space? Did they ask for the sample space? They didn't ask for the sample space. But by now we know how to get the sample space, right? So the sample space here will be I either get two who love running, or I get the one who loves running and the jumping, okay? Or I get the one who loves running and the what? And the press ups. Or I can get the one who loves jumping and then running, okay? There, or jumping and jumping. So I write jumping and jumping, or it can be jumping and then press ups. So jumping and then press ups. I think we need this on part B. So it's good that we've stated it. Or the outcome is that I can pick the one for press ups and then the one for running. So I'm press ups here and then I go to the running, or press ups and then I go to the jumping. Okay, or it can be press ups here and then I go to press ups again. So P and what? P. So this one here I'm going to say is my set S. So it's a set of all the what? The possible what? Outcomes, like that. Okay, so that is my sample space from my tree diagram. And then now I start answering part B. So part B, they're saying, okay, state whether the following are simple or they are compound events. Okay, so we said a simple event is the one that just has what? One outcome, remember? And then a compound event is the one that has two outcomes, or what? Or more. That's what we said. So if I look at this event, the first one, they're saying both like running, okay? Both like running. So is that event for both of the people that they have selected liking to run, is it simple or compound? So where can I see RR in this sample space? I can only see it one time like that. So it means we just have one outcome in this event where both like what? The running. So we're going to say that this event is what? Is simple because it just has one outcome, running. Okay. So it starts simple like that. Okay. So this one here is simple. And then part two, they've said two, the two individuals that you've selected, they like different activities. Okay, so I'm just going to say this event, the event where they like different activities. Okay, so different activities, we are going to say, we're going to get everything here that has different letters. So it can be running and jumping, running and press ups, or it can be jumping and running. Okay, or it can be jumping and press ups, or it can be push ups, press ups, I mean, and running, or it can be uh, uh, press ups and what? And jumping. So this is the event that we have when we consider this description on part 2. So is this a simple or a compound event? It's just going to be a compound event because when I look at it, it has 1, 2, 3, 4, 5, 6 outcomes, okay, from this event. So this one here is going to be compound. What about part 3? They're saying one likes running, okay? The other likes jumping. So here they've not given us any order. They've just said one likes running and one likes jumping. So it means I can start with the one that likes running, okay? And then I can also start with the one that likes the jumping, then the running. So how many events, outcomes are here? There are 2 outcomes here, okay? So we're going to say that this event is actually what? Compound as well. It's not a simple event. Okay, but now look at part 4. Part 4, they're saying the first. So here there's order. Okay, they're saying for that outcome that you should get, the first, okay, should like press ups, and then the second should like running. So here, okay, which outcome has the press ups and then the running? Okay, we just see that it's just one, this one here. So it will just be press ups and then the what? The running. So press ups and then the running. Okay, so is there anything again that starts with the press ups and then the running? No. So here there's just what? One event. One outcome. So this one is going to be called as a simple event like that. So that's how you judge. Okay, and then the fifth one, they're saying none of the two likes running. Okay, so none of the two likes running. It means to be the event that contains everything here. Okay, apart from the what? From those who have running. So you list everything that is there apart from this part here. Just list everything in this event here. That will be the one that describes the part 5 there. And then it will have more than one outcome. So I'm going to say that the last part there is also a compound what? Event like that. All right, so we are done with that part. Any questions there, guys? Okay, so let's look at another question on the sample space and then the tree diagram. Okay, the sample space and then the tree diagram. Okay, so the question says 2 employees are selected from a group having young, medium, and then adults employees. Draw a tree diagram, and then here they're saying how many possible outcomes are there. Okay, how many possible outcomes are there? So how many people do you want to select? You want to select 2. Okay, from the young, the medium, and the what? The adults. So I'm just going to say in my first selection, okay, I can have young, or I can have medium, or I can have what? The adults. So this will be my first selection here. What about my second selection? So just draw a line here to differentiate that selection, that this is now second selection. So it can happen that I pick young again, or I pick medium, or I pick what? Adult. And it'll be the same here. So you see that these things are actually very simple, right? So young, medium, adults. And here again, it can be the same. So young, medium, and then adult. Okay, so this is my tree diagram. I've drawn it. Okay, and then they're saying how many possible outcomes are there. So we just have to list the sample space. So the sample space can be young and young. So Y and Y. Or young and M. So Y and M, or it can be Y and A. Then I'm done with the ones that start with the young. So I go to the ones now that start with the medium. So it will be M and Y, M and M, and then M and A. Okay, I'm done with the ones that start with the medium. I go to the adults. So it can be A and then Y, or it can be A and then M. The last one there, I'll just put it down here. It can be A and then A. Okay, so these are the possible outcomes. We've listed the sample space. So now let's count how many are there. So 1, 2, 3, 4, 5, 6, 7, 8, and then 9. So there are 9, okay, possible outcomes in total. Okay, so any questions there, guys? Okay, so thank you so much. I'm very sure that you are enjoying this video and you are understanding the concept. So I'd just like you to inform you that we actually have a platform, okay, where we have a lot of videos that can help you understand, just like the way you've been understanding as you've been watching this video. Okay, so the platform is called discretelearning.com. So you can actually visit our website. So here, just search discretelearning.com here, and then you click search. It's going to take you to this website. If you don't have an account, just create one. Okay, you can check the link in the description here. It has a video that can help you create an account. Then once you log in, okay, using your details, you find these are 4 pre-med courses or NS courses. So there's math, chemistry, and biology. Okay, so you can subscribe for any course here, and then you're going to find a lot of videos. Okay, tutorial sheets, you're going to find topic lessons, and you're going to find past papers, and all that is going to help you in your studies. All right, so if you're interested, please make sure you subscribe and then be learning at your own pace. Okay, so now in this video, we are going to look at basic probability calculations, and we have these questions here. Okay, 3 of them that are going to help us understand the basic probability calculations that do not necessarily involve tables, but they just involve basic equally likely outcomes, the complement rule, and some independent selections. Okay, so these independent selections, we're going to be finding them on the tree diagram. Okay, and then from the tree diagram, we're going to see how we can use the probability rule, the multiplicative rule, sorry, not the probability rule. How we can use the multiplicative rule to actually find the what? The probabilities. Okay, so the first question here, they're saying 2 babies are born at a clinic on a particular day. Find the probability that both are baby boys. Okay, only one of the 2 is a baby girl. The babies have the same gender, and the babies are of different what? Gender. So now, if you go back to the classical definition of what probability is, okay, the classical definition of what probability is, we said if we want to find the probability of A, okay, I want to find the probability of A, then this will just be the favorable outcomes, okay, okay, favorable, how do you write favorable? Okay, so favorable outcomes, and then divided by the what? The total number of outcomes. Okay, total number of outcomes. This is the classical definition of probability. Okay, you just divide what is favorable by the what? The total. So if, for example, in your class, you have 10 females, okay, and then you have 10, let me say 5, 5 males, okay, what is the probability of choosing a male? Just going to say probability of the male is, okay, what are the favorable outcomes? So there are 5 males there. And then what is the total number of people that are there? So you add the 5 plus the 10, you get your 15. Then when you divide here, that's when you find the probability, right? So this is the classical definition of probability. So now, for me to find the probability that both babies are boys, I need to find, okay, my favorable outcome. And I also have to know the total number of outcomes for that particular situation that they are describing. So here, it will take us back, okay, to um, writing first of all the sample space so that we know the total number of possible outcomes for that situation. And then based on the sample space, we can tell the probability that both of the babies are what? Are actually boys. Okay, so um, sample space will just be equals to, if you want, you can draw a tree diagram, okay, to show it. But I'm just going to say it can be in this way. It can be that the two babies that I'm selecting, they are both boys. Okay, so it can be BB there. Or, in fact, I should be representing these as pairs. It can be that I select a boy and then a boy again. Or I can select a boy and then a girl. Or it can be that my first selection was a girl and then I select a boy. Okay, or it can be that I select a girl and then a girl again, like this. So this is my sample space. Okay, the total number of possible outcomes. So now if I go back on A, the probability that both are boys. Okay, probability that both these babies are boys will just be what? So what is the number of favorable outcomes that I can see here? How many BBs can I see here? I can only see one B. And then divided by the total number of outcomes in this sample space are 1, 2, 3, 4. So this is just going to be 1/4. And that will be our answer there. So the probability that both babies are boys is just 1/4. Okay. What about B? So B, they're saying find the probability that only one of the two is a baby girl. So only one of the two is a baby girl. It means that the other one should be what? Should be a boy. Okay, so I'm finding the probability. Okay, I'm finding the probability uh, of only one is a girl. Okay, only one is a girl. So what do you think about this probability? Okay, so when I go to my sample space here, which pairs are showing that there's one girl there and then there's also one boy there? Okay, you can see we have this part and this part. So it means the number of favorable outcomes are just going to be 2. Okay, because I have this and this. So I'll say 2 over the total number of outcomes, which is 4, but I can reduce this to 1 over what? 2. So my probability there of only one girl is a baby girl. Uh, of one of the two is a baby girl, it's 1 over what? Over 2. Okay, what about C? They're saying probability that the babies have same gender. Okay, so same gender simply means they are both boys or they are both what? Girls. So when I go to my sample space here, where can I see both boys and both what? Girls. You can see here 1 and then 2. So it means the number of favorable outcomes from the sample space is just 2. And then I divide by the total a number of outcomes, which is 4. And this is just going to give me 1 over what? Over 2. Okay, and then we look at part D there. So part D, they're saying, okay, we're finding the probability that the babies are of different gender. Okay, so now I should ask the question here. The probability that the babies are of different gender, I mean. What's the difference between part D and part B there? What's the difference there? Is there any difference there? On part B, they said only one of the two is a baby girl, meaning the other one should be a boy. And then on D, they're saying the babies are of different gender. So what's the difference between those two statements? Okay, so there's no difference there. So the same answer that we got on B is the same answer that we are going to get here. So I'm just going to say different then. Okay, so different gender simply means I can pick a pair that has boy and girl or girl and boy, and they're two, and then divided by the total, and I'm just going to get 1 over what? Over 2. Okay, so um, that would be my probabilities there. So we found all the probabilities there. Unless there is a question I can answer to it. Okay, so let's move and look at this question here. Okay, so the question says the probability that a pupil is sick is 0.75. What is the probability that the same pupil is not sick? So now here we're just using the law of total probability, right? So the total probability should always be equals to what? 1. So if the probability of this guy being sick is 0.75, what is the probability of him not being sick? So when you add the probability of being sick and the probability of not being sick, should give you 1. Okay, so I'm going to say probability, okay, of sick plus the probability of not sick should give you what? 1. Okay, should give you 1. So if this is 0.75, then what is the probability of not sick? Okay, so you see what we are going to do here will just be probability of not sick will be equals to 1 minus 0.75. So this will just be 0.25. So the probability of not being sick is just 0.25. So what we are using here is what we call as the complement event. So remember in set theory, in first semester, what we did was that if I have a universal set U here, okay, and then let's say this universal set has 1, 2, and then 3, and then I have a set A which just has 1 and 2. And then I'm asked to find my A complement. What were we doing? Okay, the A complement will just contain all the elements that are not part of set A, but they are part of the what? Of the universal set. So that will just be 1. That will be my A complement. So now you see that if I add my A complement and my A, I should get back my what? My universal set. So this is the situation that we are doing here. So now when it comes to probability, and then we are trying to use this same analogy or logic, okay, we're going to say universal set is the same as it's the same as the set A plus the set what? A complement. Okay, so now if I want to find A complement, I'm just going to say that is universal set minus what? A. Okay, I've just taken this guy to the other side, and then I'm just written the A complement as the first one. Okay, so now from here, let's take probabilities of everything. So I take the probability of this. I also take the probability of this. I also take the probability of this. Okay, so see what I have now. So it will be the probability of A complement simply equals to what is the probability of the universal set? So the universal set is the same as the sample space. Okay, so the probability of the sample space, since you are considering everything, will always be equals to 1. So the probability of this universal set, which is the sample space, is just 1. And then minus the probability of what? A. So this one here is what we call as the complement formula, or the complement what? Rule in probability. So most times, okay, if you have such questions there, just apply the complement what? Rule, like this one. So I'm just going to say, okay, the event that this guy is sick is A. And then meaning that the event that is not sick is the A complement. So the probability of A complement will just be equals to 1 minus the probability that is sick, which is A. So that is 0.75. And then you have your 0.25 as well, like that. So I've explained it in 2 different ways so that you just get it clearly like that. Okay, so I hope this is clear. Okay, I'm sure. So I'll move on to part 7, or just the next question. So here, okay, we need to draw a tree diagram in order to answer this probability. And such a question here, it's similar to the one that we had in secondary, grade 12. So they like to bring such a question here. So they're saying the probability that an individual is allergic to a certain medication is 0.32. Three individuals are selected randomly. What is the probability that all the three are allergic to this medication? Only two are allergic to the medication. None of them is allergic to the medication. Only one is allergic to the medication. So we still use the complement rule here, right? So this is the probability of being allergic. So let's say allergic is the event A, okay? And then the complement of these events, it can be a complement, okay? But here, let's just represent it as N, or not allergic, okay? So A complement is the same as not allergic. So we said, if I want to find the probability now of the complement, which is just N, it will just be 1 minus the probability of the what? Of the event A. So this will be 1 minus 0.32, and this will just give me 0.68. So the probability of being allergic to a certain medication, it's 0.32. Then the probability of not being allergic to that medication, we found that it's what? 0.68. How did you find that? We use the complement rule, because we know that if I add the complement, the probability of being allergic to the probability of not being allergic, then I should get a 1. All right, so now let's draw a tree diagram. And this time, the tree diagram that we're going to draw is going to have probabilities in it. Okay? It's going to have probabilities in what? In it. Okay, so here, what have they said now? Okay, so here they've said there are three individuals. Okay, three individuals are actually selected at what? At random. Okay, three individuals are selected at random. Okay, so let's draw the tree diagram here. Okay, because later on you're going to see that you can actually answer this question way easily by just using the binomial distribution. But we haven't yet learned the binomial, so we can just use that tree diagram. So I'm going to say first probability there. Okay, so let me spread this a bit like that. Okay, so what I have here is that I have three. Oh, no, 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 no. I shouldn't have three tails here. I just have two, because it's just allergic or not allergic. So I have this and then that. So this is allergic, and then this is what? Not allergic. Okay, so that is what I have there. So we are saying that the probability of allergic is what? 0.32. And then we find that the probability of not allergic is actually what? 0.68. So now remember, I'm selecting how many individuals? Three individuals. So meaning this one here is just my what? My first selection. So it means there should be a second selection. So if my first selection was a person that was allergic, then my second, okay, will be that maybe again I select the person who is allergic. So the probability is the same there. Okay, because we haven't been told that the events are happening with replacement, or the events are happening without replacement. So we assume they're just constant. Okay, so here it will be the probability of not allergic, which is 0.68. Okay, and here again to be a similar thing. So not allergic, allergic, probability of allergic 0.32. Probability of not allergic 0.6 what? 8. Okay, so this one in red here is my second selection. So I've picked how many individuals so far? One here and then two there. Okay, so I have to make a third selection now. Okay, so let me erase this. So the third selection will be here. I can go two ways. I can have another allergic again, or I have not allergic. Here, I have allergic, not allergic. Here, I have allergic, again, not allergic. And then here, I have allergic, not allergic. So this selection in green is my third selection. Then once I'm done with this, then I have my three individuals, right? So now the probabilities, we're saying, yeah, we're assuming that they remain constant because we haven't been told if this selection is happening with replacement or without what? Replacement. Okay, so we just assume they are constant there. So this is 0.32, 0.68, 0.32, then 0.68, like that. Okay, so this is my tree diagram. And then from the tree diagram, I should be able to find the probabilities that have been given there. So the first one is find the probability, okay? Okay, find the probability that all three are allergic to this medication. So if they're allergic, it means here I'm getting this probability, with that probability. So now these selections are actually independent, because if you are allergic to this particular medication, it does not affect your friend, right? Okay, it does not affect your friend. Your friend has a totally new system in their body. Okay, their cells are behaving different. So whether they are allergic or not does not depend on the other person. So it means the selections are what? Independent. And we said from the definition that if two events are independent, okay, then we can just find their intersection by multiplying their individual what? Probabilities. So I don't know if you remember this when we are defining things. Said if these are independent, then it's the same as probability of A multiplied by probability of what? B. Because here we're finding the probability that all the three are actually allergic. So you see, we are finding the probability of the first person intersection, the second intersection, the what? The third. And we know that these are independent. So we're just going to multiply their individual probabilities. So probability, okay, this one here, that all the three are actually independent. You can say probability of all three allergic, I mean, not independent. All three allergic is going to be equals to this multiplied by this multiplied by that. So I'll just do that on my calculator. So 0.32 multiplied by 0.32 multiplied by 0.32. Okay, so my answer that I'm going to get there is simply showing me 0.032768. Okay, so that is the probability that all the three individuals that I select, they actually what? Independent. Ah, why am I saying independent? That all the three are allergic. Sorry for that. Okay, and then part B, they're saying what is the probability that only two are allergic to the medication? So only two are allergic. It's going to differ the path that you're going to take. Okay, because remember we're selecting three individuals. So only two are allergic. It can either be the first is allergic, the second is allergic, and then the third is not. Because we are just saying only two are allergic. So it will be the probability of A, and then N, okay, plus it can be the probability that this one is allergic, and then not allergic, and then allergic. Okay, so it will be probability of allergic, not allergic, and then allergic plus. It can also be what? It can also be the probability that the first one is not allergic, and then the two that follow are allergic, like that. So it will be plus the probability of not allergic, and then allergic, and then allergic. So these are the probabilities that we have to find. So to find the probability of allergic, not allergic, we're just multiplying allergic multiplied by not allergic. Oh, first allergic multiplied by allergic, and then multiplied by not allergic. So we find this. Okay, and then we say the number that we're going to get here plus the probability of allergic, not allergic, and then allergic. Okay, so I'll just be doing that on my calculator. Okay, so let's start with this one here. So probability of allergic, and then not allergic to be 0.32 multiplied by 0.32 multiplied by 0.68. So that will give me 0.069632. Okay, what about this probability? Maybe I should be writing it there so that it fits 0.069632. What is the probability of allergic, not allergic, and then allergic? So allergic, not allergic, allergic. So 0.32 multiplied by 0.68 multiplied by 0.32. You see, I'm just going to get the same answer here because I'm multiplying the same probabilities. And even here it will be the same because this is 0.68 and then 0.32, 0.32. So I get the same. Okay. And then I just add them now to get the final answer. So the probability of only two are allergic will be the addition of these three here. Or you simply say this one multiplied by 3. So when I do that, I get my final probability on part B to be 0.2088 and then 96. And then I'm done. Okay, so that is part B. And then part C, they're saying none of them is allergic to the medication. So none of them is allergic to the medication. What do they mean? Okay, none of them is allergic to the medication. They simply mean uh, all the three are not allergic. Okay, because none of them is allergic. So to find that, it will be the probability of n, n, and then n. So I'm just multiplying this, with that. So what do I get when I do that? I'm getting 0.3144 and then 32. So this is the probability of none of them being allergic. In short, the probability of not being allergic. Okay, so any questions there, guys? Okay, let's look at the last one. So the last one, they're saying find the probability, okay, that only one is allergic. Okay, find the probability that only one is allergic. So let me erase some of these things here. Okay, so only one is allergic. It means I have which combinations now? So only one is allergic. It means of those three, only one should be allergic. Okay, so where can I find those combinations where there's only one is allergic? So it can either be what now? Okay, it can be allergic and then not allergic, not allergic. So there's only one who is allergic. Okay, or it can be not allergic, not allergic, and then allergic. So there's only one again there. Okay, so I'm going to add um, uh, those. Is there any combination there where I also get one allergic to be in the sequence there, apart from those two that I've identified? Because they're saying only one is allergic. So if this is allergic, okay, then this guy is not allergic, and then this guy again is not allergic. I have one. Okay. What about if I have not allergic, okay, and then uh allergic, and then so I see another combination here. So the first one is this one: allergic, not allergic, and then not allergic, plus probability of not allergic here, okay, and then allergic, and then not allergic. So I've moved not allergic, allergic, not allergic. Okay, and then plus the other one is the probability of not allergic, not allergic, and then allergic. So these ones are the one that satisfy the condition. Only one is what is allergic. Okay, and you see that these are just going to give me the same probability. So to get this answer, you just find for one, then you multiply by 3. So let me multiply the one for allergic, not allergic, not allergic. So it will be 0.32 multiplied by 0.68 multiplied by 0.68. Okay, so I'm going to get 0.14768 68. Then I multiply this by 3, sorry. So my probability there will be 0.4430 4 like that. Okay, so that would be my probability there. So any questions there? Okay, so thank you so much. I'm very sure that you are enjoying this video and you are understanding the concept. So I'd just like you to inform you that we actually have a platform, okay, where we have a lot of videos that can help you understand, just like the way you've been understanding as you've been watching this video. Okay, so the platform is called discretelearning.com. So you can actually visit our website. So here, just search discretelearning.com here, and then you click search. It's going to take you to this website. If you don't have an account, just create one. Okay, you can check the link in the description here. It has a video that can help you create an account. Then once you log in, okay, using your details, you find these are 4 pre-med courses or NS courses. So there's math, chemistry, and biology. Okay, so you can subscribe for any course here, and then you're going to find a lot of videos. Okay, tutorial sheets, you're going to find topic lessons, and you're going to find past papers, and all that is going to help you in your studies. All right, so if you're interested, please make sure you subscribe and then be learning at your own pace. All right, so welcome to this video. We are going to be looking at probability questions on two-way classification tables. Okay, so these ones are also what we call as the contingents tables. Okay, so these ones here, okay, I must emphasize, these ones, they don't miss in the assessments. Okay, so meaning in your test one, such a question is going to come. Okay, and in the final exam, also, such a question is going to come. Okay, so you're just finding probabilities using a table. So whenever you see a table and then you're asked to find probabilities, then just know that those are free marks. Okay, you should be smiling because they are the simplest questions that you find in the exam. Okay, so let's go through this one. We see how simple it is. So they're saying 2,500 people. Okay, so maybe I should write that number somewhere. Okay, so they're saying 2,500 people, okay, in a certain town were asked if they were immunized against measles or not. The table below summarizes their responses. Okay, so this is a immune state. Okay, and then this side here I have the gender. Okay, so gender going down, the immune state going to the right like that. So it's either they're immunized, not immunized, or they're unsure. They don't know if they were actually what? Immunized. All right, so for the people who were immunized, we had 520, we had 520 what? Males. And then we had 620 females. For those who are not immunized, we had 480 males and then 380 females. For those who are unsure, okay, we had 330 males and then 170 what? Females. Okay, so the first thing when you just see a two-way classification table is to make a box for the total numbers. So I'm just going to say something like this. Okay, so okay, something like that. Okay, so okay, eh. Okay, something like that. So in this now, you're going to write total there. Okay, and then you just start adding. So in this column, how many people did we have? You add the males and the females or whatever you are considering. Okay, because it will not always be males and females. It can be any other thing. So 520 plus 620. I'm going to get 1,140. And then here, I add 480 plus 380, I'm going to get 860. Okay, then here for unsure, 330 plus 170, I'm going to get a 500. Okay, so now you have to add these numbers to see if they're going to actually give you the total of 2,500 people. So let's add 1140 plus 860 plus 500. Okay, I'm going to get the same number, which is just 2,500. So this shows that you're doing the correct thing. So even here you put total again, and then here you'll be adding in this direction like that. So I add 520 plus 480 plus 330. So here I'm going to get 1330. Then even in this row, I add. So 620 plus 380 plus 170. So I'm going to get 11 and then 70. So if I add those two numbers, I'm also getting 2,500. So I'm good to go. Okay, so the first thing is always to complete the table, like the way I've done. And then now you start answering the questions. Okay, so the first question says, a person is selected from these 2,500 people. What is the probability that the person is male? So, probability that the person is what? Male. Okay, so just use the classical definition for probability. We're going to say the number of favorable outcomes over the total what? Outcomes. Okay, so you can see that how many males do we have there? So you go here in this row for the males. You go at the end there. That is the total number of males. So I'm just going to say 1330 divided by the total number of people that are available here are just what? 2,500. So 2,500. Okay. If you want, you find a decimal number there. So just divide that on your calculator. So 1330 divided by 2,500. So that will give me my probability of 0.532. So this is the probability that the person selected is male. So 0.532. Okay. Probability that they are immunized. So immunized, I'm going to use I. So it's just the total number under immunized here, which is 140 divided by the total number of people present. So 200 and 2,500 there. So it will be 1140 divided by 2,500. So this will just be 0.456. Okay, so here I'm going to write 0.456. Okay, and then now we come to the interesting part. Okay, so I can erase this. So we come to the interesting part, which will be combining events. Okay, we'll be combining events. So look at what they're saying now on part C. They're saying find the probability that this person is not immunized and is a female. So the word and in probability or in set theory, we said and means what? Intersection. Okay, so we're just trying to find the probability of not immunized intersection what? Female. This is what we are finding there. Okay, so I'm going to say, how can I find this? So what is the total number of favorable outcomes? So I'll just go to the part that has the intersection of not immunized and then the female. So how do I do that? I just go to not immunized, I draw a line, and then the female, I also draw a line. Okay, so I should be drawing straight lines here. So in the females, I draw a line like that. Okay, and then in the not immunized, I also draw a line. So in the box where these two lines are going to cross here, that's where my intersection is. So you've seen this part here. Okay, so in this box here, that's where my intersection is for the not immunized and the what? The female. So meaning that I'm just going to get that same number. So here, so that would be what? 380 divided by what? The total number of people that are available, which is just 2500. So if I punch this on my calculator, to be 330 divided by 2500. So that will give me 0.152, like that. Okay, so it means that I've actually found my probability there. So the probability here is just 0.152. Okay, so I'm done with that. I move to part D. If there are no questions. So part D now, what are they asking us to find? Okay, so part D, they're saying find the probability that this person is either female or unsure. So we said in set theory, and we're going to say this the same thing in probability theory. If I have either, then if I have or, then I'm talking about the what? The union, right? Okay. If I have or, then I'm talking about the what? The union. So I'm trying to find the probability of female, okay? Union what? Union unsure. So unsure, we're going to write Uh, since I'm using the union here as U, for unsure, I'm just going to write S. Okay, so probability of female union unsure will just be what? So here we'll just use the addition rule, okay, for probability. So this will be the same as the probability of female plus the probability of unsure, then minus the probability of female intersection what? Unsure. Okay, so meaning we just have to find these individual probabilities and then we get our answer. So probability of female will just be the total number of females, which is what? This guy here. Okay, so now I've erased the total here for everything. So here there was the 2,500. Okay, and then here there was a 500. Okay, so the total number of females, it's 1170 divided by 2500 plus the total number of unsure, I come in this column here, it's just 500. Okay, it's just 500. So it's 500 over 2,500 minus the total number of people in the intersection, okay, of female unsure. So it's unsure and then the female. So they meet here. So it will just be minus 170 over 2500. So this will be what? So since the denominators are the same there, I'm just going to write one denominator and then I'm just going to add and subtract whatever is on top. So 1170 plus 5 zade minus 170. So that will just be 1500. And then I divide this by 2500. Okay. So 1500 divided by 2500. So I'm going to get my probability as 0.6. So this is the probability, okay, that the person selected is either female or unsure. So I'm going to write there 0.6. Okay, so now let's do some conditional probability. So the next one, they're saying, find the probability that the person is male given that he is unsure. So this is the probability of male given that he is unsure, like that. So this one we said by definition it's just the probability of M intersection S and then divided by the probability of what? S. Okay, this is what we are saying. So this will just be equals to, so the probability of M intersection S. So unsure is here, the male is there, so the intersection is there. So it will be 330 divided by the total. Okay, and then this divided by the probability of unsure is just 500 over what? 2500. So you can just simply punch this on your calculator. So put this in brackets, okay, to avoid wasting time. Put this in brackets, then divided by, put this in brackets, then just punch on your calculator. Okay, it should be able to give you the answer there. So the answer there would just be what? 0.66. and that will be my probability. Okay, that will be my probability. Okay, so I'm just going to write here on E, that will be 0.66. Okay, and then part F, what is the probability that the person is unsure of the immune given that he is male? So now we are like finding the opposite of this. Okay, we're finding the opposite of this. So we're saying the probability of unsure given that he is male. So this will just be the probability of unsure intersection male divided by the probability of what? Male. So it's just the same thing. So the intersection of unsure and male or male unsure is the same as 330 over 2500. Then I divide this by probability of male. Probability of male, how many males do we have? Okay, this is the total of males there. So 1330 divided by divided by 2500. Okay, so I said it without wasting time, punch this on the calculator in brackets, divided by this on the calculator in brackets. So what you're going to get there will just be 0.248. And that will be the probability of unsure given that he is what? He is male. So I can write it there like that. Okay, so any questions there, guys? Okay, let's look at the last two questions there. So the last two questions are saying, are the events male and female mutually exclusive? Okay, how about female and immunized? Why or why not? Okay, so we start with the male and female. So he said if two events are mutually exclusive, then it suffices to show that their intersection is what? 0. Okay, so the first one there, I'll just say probability of male intersection female will be equals to. So is there any point here where the males are intersecting with the females? There's no way, because if I draw a line in the male, I also draw a line in the female, you see that these lines do not touch each other, right? So it means that in this intersection, there is 0, and then I divide by the total number of people, which will just be 0. So if the probability of their intersection is 0, then we have shown that male and female are mutually exclusive events. Okay, mutually exclusive. So they're mutually exclusive. There is no intersection between them. Okay, what was the other one? How about female and immunized? So if I draw a line in the female and then I draw a line in the immunized, you see that they are going to meet somewhere there. So it means these ones are going to have an intersection. Okay, so I'm just going to say um, probability of female intersection immunized is just going to be, so they intersect here. So that is 620 over 2500. And this is not going to be 0. Okay, this is not going to be what? To be 0. So 620 divided by 2500, I'm going to get 0.248. And you see that this probability is not equal to 0. So since this probability of their intersection is not equal to 0, then we can conclude that female and immunized are not mutually exclusive. Okay, so make sure you know how to do this because it's definitely coming in your what? In your test 1. Okay, there's no excuse. This question is always there in test 1. Okay, they'll just change the numbers, change the thing they're asking you about, but the concept definitely the same. All right, so we've said here why, and here we've said why not. What about the last one there? They're saying explain mathematically why events male and unsure are not independent. So now we are talking about independent events. So he said two events are independent if their intersection, the probability of their intersection is equal to the product of their individual probabilities, right? So here I have male intersection unsure is equals to probability of male multiplied by probability of unsure. So if this is true, if this probability is equals to this, then I'm going to say they are independent. Okay, that's how we show mathematically. If they are not equal, then we're going to say they are not independent. So probability of male intersection unsure would just be what? So this is the male and unsure where they're intersecting. So 330 over 2500, the total is equals to, uh, the probability of male is 1330 over 2500 multiplied by, unsure, the total is 500 over 2500. So we can already see that this won't be the same. Okay, we can already see that this won't be the same. So if I divide this, I'm going to get 0.132 is equals to, okay, so if I multiply this, multiply by that, first of all, this one here, okay, gives me 0.532 multiplied by this probability here gives me 0.2. So now if I multiply this, I get 0.1064. And you see that this part here and this part are not equal. Okay, so if this part is not equal to this one, then we have explained mathematically that the male and the unsure are what? Not independent. Okay, so any questions there? Okay, so I hope you're understanding it. Okay, so let's look at the last question and then we call it a day. So let's look at this next question here. So they're saying HIV test might be tricky. It may show positive results when an individual does not have the virus, which means false positive. It may also detect a negative when a person actually has the virus, so that is false negative. A test on 60 individuals gave the following results. So here they have the HIV virus and then they test positive, and then here they test false positive, which is indicating negative, and whatever the table is saying there. So I said whenever you have a two-way classification table, you always have to draw the column and the row for the what? For the total. So I'm going to say here, okay, we have the row, and then there we have the column for the total like that. Okay, so this is what we have. Okay, so I'm going to say total here and also total there. Okay, so let's add to see if we are going to get the 60 there. Okay, so if here I add, I have 30. In fact, there they already gave me the total, right? What was I doing? So here they already gave me the total. So I just have to add the total for the other part. Okay, so here I erase this. It's not needed. Okay, because they already gave me the total. So I just have to find the totals for this. Okay, so 3 plus 30 in the first row, I have 33. And then in the second row, 3 plus 24, I have 27. So 33 plus 27, I get 60 indeed. Okay, that is good. Okay, so now that we have the two-way classification table, we can find the probabilities. So A, what is the probability that an individual tested false positive? Okay, so false positive means they have the virus there, but here they test negative. That's what? False positive. Okay, so how many individuals are in the false positive? So A, probability of false positive. Okay, so how many individuals tested false, but they actually had the disease? We see that it's just what? 3 there. So it will be 3 over the total 60. And if I punch this on my calculator, I get 0.05. Okay, B. What is the probability that an individual tested will test positive given that they have the virus? So probability of testing positive given that they have the virus. Okay, so if they have the virus, it means I'm just saying probability of positive given that they have what? The virus. Okay, this is what I'm saying here. So this false positive here, you can also indicate it by n if you want. Okay, so this will just be the probability of positive intersection virus, okay, divided by probability of what? Virus. So what is in the intersection of the positive and the virus? So positive is here, virus is there. So these lines meet here. So that is 30. So it will be 30 over 60 divided by how many have the virus, the total. Okay, so have the virus, the total is at the end there, which is just what? 33. So I'm going to say 33 over 60. From here, what do? You go on your calculator without wasting time. Put this in brackets and then divide by this in brackets again. So your calculator there will give you approximately 0.909. Okay, so another question that can come here, because this is the answer that we get when we find the probability of testing positive given that you have the virus. This here as a special name, okay? And we'll see it in future questions. It's what we call as the sensitivity, okay? We call it as the sensitivity of the test, okay? So sensitivity of the test is simply the probability that the test shows positive given that you have the virus. Okay, that is called sensitivity of the test. So sometimes they just say the sensitivity of the test is this. So in your interpretation, you have to know that, okay, sensitivity means the probability of positive given that you have the virus. Okay. Okay, so I thought it was important to mention that. And then part C, what are they saying now? Okay, but see, they're saying find the probability that the individual tested have the virus and they test positive. So this is different from what we have on B. So this is probability of the virus intersection P. Okay, which was just this guy here because P intersection V, V intersection P is the same. So it's 60 over 30 over 60, and this here will just be 0.5. So this is the probability or that they have the virus and they test. Okay, it's different from B where we are saying given. Okay, because that is a conditional probability now. What about D? So D, they're saying what is the probability that an individual tested has negative results given that they have the virus. So there, we're also talking about uh, conditional probability. So I'm going to say probability of, okay, they said has negative results given that they have the virus. So this will just be probability of negative intersection virus divided by probability of what? Virus. So this will be, where's the intersection of negative and virus? Virus is there, negative is there. So it's in here where they have 3. Okay, so I'll just say 3 over the total 60 divided by the total for the virus is 33 over 60. So this will just give me, okay, this will just give me, so don't waste time here, just put in brackets 3 over 60 divided by 33 over 60 on your calculator. So that one is going to give me 0.091. So check with your calculator as well to confirm the answer. All right, so we move to B now. B, they're saying, are the tests results being positive and having the virus independent? Explain numerically, okay? Are the test results being positive and having the virus independent? Explain numerically. So explain numerically, explain mathematically is the same. Okay, so here we're just trying to see if being positive and having the virus is independent. So we find or check if the probability of positive intersection virus is equals to the probability of positive plus, not plus, but multiply, okay? Multiply by the probability of what? Virus. So the probability of positive intersection virus. Positive is here, the virus is there. So that is just 30 over 60 is equals to probability of positive. Positive, the total is there, 33. So that would be 33 over 60 multiplied by virus. I have 33 again over 60. So is this the same? Definitely it's not. Okay. So on my left, I have 30 divided by 60, which is 0.5. Then on my right, I have 33 divided by 60 and multiply by 33 divided by 60. So if I punch this direct on my calculator, I'm getting 0.3025. So you see that the left and the right are not equal. So if they are not equal, then we've shown numerically that they are what? Not independent. So you say that since, okay, the right-hand side and the left-hand side are not equal, okay, then the two events are not independent. Okay, so that would be your conclusion on part B. All right, so it means we've reached the end of this video. Okay, so here they're saying, what brief explanation can you give to an individual testing negative for HIV? Okay, what brief explanation can you give, okay, to an individual testing negative for HIV? Okay, so what you'd say is that from the table, among those with the virus, okay, the 33 people, because here there's 33 people. Among those with the virus, the 33 people, 3 actually tested negative. So I'll explain to this individual that false negatives do exist because those people have the virus, but they're testing negative. Okay. And then I'll give a short explanation just such that a negative result does not guarantee that the person does not have the HIV. Okay. Because the test sometimes produces false negative. And in this case, we can see 3 out of the 33 infected individuals tested the negative despite them having the what? The virus. Okay, so meaning that this test that we are actually conducting is not 100% what? Accurate. So if the person really wants to know their status, then you would encourage them to do the test uh, more than once. Okay, you ask them to do the test more than once so that if the first one lied, maybe the second one can tell the correct story. All right, so that's how you can answer part C. I don't know if there are any questions from you guys. All right, so thank you so much for watching this video. Come to the end of the video. And if you'd like to access the full video solutions of all the questions that are here, okay, you can subscribe and you'll be able to find them on our website, which is discretelearning.com. And you can also actually install our mobile app. So on our mobile app, all the videos that are there, you can actually download them. So let me just show you the website. So just search discretelearning.com. Click search. If you don't have an account, just simply create one by putting your details. So your name, your email, your password, and then boom, you log in with those same details. You're going to be taken to this page where it has our courses. So here there are all the courses that we offer. Okay, so all these courses we offer them: medical biochemistry, human anatomy, physiology, biostatistics, whatever course is here, we actually offer it and you can subscribe for it. Okay, but for this video, let me just show you how you can access full solutions to that tutorial sheet. So you just open the folder mathematics, okay? That is if you're doing second semester at Apex. Okay, but if you're doing a probability at any other university, which is not listed here, okay, then you have to look for the course that is written statistics and probability on the courses there. Okay, and then you're going to find or whatever you're looking for. So I just come here and click here on Apex second semester. Okay. And then just wait for it to load, and then you can see tutorial sheets here. Click on the tutorial sheets. Okay. You are going to see that you have the 2026 January intake or any intake that you belong to. In case you're watching this video in the future, you find a folder for your intake. So click on it. Okay. You can see, oh, so it's loading there. So you just wait for it to load. Okay, so now you've seen that it has loaded. So there's tutorial sheet one, full videos on statistic. Then there's tutorial sheet two, full videos on probability. So you can access those and use them to learn at your own time. Apart from that, we have past papers. So quizzes, tests, exams, they're there. So you can just click there and find the videos for the test. So you can use this to learn at your own time. Go to the videos at your own pace, even in your what? Even in your blankets. Okay, so you can see there are a lot of exam papers, quiz papers, and test papers that have been solved here, and you can access them and they can help you prepare for what? For your assessment. Okay, so thank you so much for watching. This has been Tutor Pro Solutions. If you want to contact me, okay, you can simply contact me on 0779 96 40 10. Okay, so that is Tutor Pro Solutions. You're going to find me on that line. Okay, if you want to subscribe on your own, you can just check the link here below. Okay, so there's a video there in the description that is going to help you create an account and pay, okay, for the course of your choice without needing anyone. So the system will grant you automatic access. You'll be able to access all this and pass your exams easily. Okay, so until next time, this has been to the Post Solutions, always there for you.